Hello, in this presentation we will tell you about the Samsun rocket team, the Kızılırmak V10 and the test launch we made. First of all, Samsun rocket team has 8 members. Our team consists of aerospace engineering and mechanical engineering students from Samsun University and 19 Mayıs University. We would like to thank all our sponsors for their support in the production and test launch of the Kızılırmak V10. Here you can see the task distribution of the team members. Although the names you have seen are the leaders of the subsystem, all members of the team, including our advisor, have been actively involved in all subsystems. The distribution of tasks in the test launch is you can see on page 5 and 6. The Kızılırmak V10 is designed for 10,000 feet in the open rocket software. We can divide the outer body into 4 main parts. These are nose section, avionics section, rescue section, and engine section. Drag parachute, parachute, and payload are positioned inside the first body part. Next comes the avionics section, and flight computers are located in this section. The main parachute is located in the upper part of the engine compartment. The engine is in the engine compartment. Here we see the graph of altitude, vertical velocity, vertical acceleration versus time. We got from the simulation made in open rocket software. According to the simulation, the maximum altitude is 2,850 meters. Here we see the graph of altitude, total velocity, and total acceleration versus time, which is again taken from the simulation. Here is the graph of stability of the rocket versus time, and as you can see, the rocket is prevented from being too stable. The values in the chart on the previous page are explained here in order. Here, the data in the previous graph are tabulated, and the maximum altitude is seen as 2,854 meters. We obtained the data of our rocket in 3 different ways. These are the telemetry system produced by our team, the altimeter 2 device mounted on the rocket, and high sensitivity radar of our sponsor Rocket. Here we see the data we received from the altimeter 2 device, and maximum altitude of our rocket is seen as 2,831 meters. The data appearing here is detailed in report. In this table, we see the data we received from high sensitivity radar device, and the maximum altitude appears to be 2,908 meters. You can access all these data on the report.
In this section, system flight analysis data will be explained. While performing this flow analysis according to the data obtained from Open Rocket, the maximum speed the rocket will reach and the atmospheric conditions at that height are taken into consideration. In the meshing part, before starting the mesh phase, a suitable size enclosure is added and the mesh phase is started. Firstly, inflation is added, first layer thickness is selected as inflation options. And with the calculated value plus value, the first layer height is decided to be 0.1 mm and to consist of 4 layers in total. Then, face and edge sizing is given noise cone, fins and both tail parts. While doing this, the quality values are constantly checked and the mesh stage is completed, especially when the orthogonal quality and the schemes value are within the correct range. The correct name selections are made and the setup phase is started. Some images from the mesh stage are given in these figures. In the setup part of this analysis, pressure base is preferred and the flow is resolved as steady. Ideal gas conditions have been selected and energy equations have been activated. Analysis is made with several different solutions methods, and it decided to perform the analysis with K omega SST considering the convergence values. Inlet velocity inlet outlet is selected as pressure outlet. In the result sections, in this analysis 4,000 iterations are made. Drag coefficient and drag values are calculated. The resulting drag coefficient values is 0.2949 and the drag value is 211.4061 Newton. When the pressure and Mach contour are examined, it is seen that the flow on rocket is quite smooth and it is seen that the flow accelerated at the wing tips and the boat tail. The Mach number contour, static temperature contour, total temperature contour, static temperature contour, total pressure contour, and density contour obtained as a result of the analysis are shown in these figures.
The Samsun rocket team uses a solid commercial rocket motor in the Kızılırmak V10 rocket. The team chose Cesaroni Technologies M2150 series motor. The rocket motor was supplied by Rocket Sun Company. According to values obtained from altimeter 2 and radar data during the flight of Kızılırmak V10, the motor is burned out for approximately 4.4 seconds. This value is different from open rocket data, but the total impulse does not change. The nose cone, rocket body, and fins are manufactured by composite production method. The first body tube, the avionics section, and the motor section 1 are made of glass fiber that can transmit signals. Motor section 2 is made of carbon fiber for withstand the thrust generated by the motor and the forces on the fins. For the production of fins, hand layup and vacuum infusion was applied. The fins coming out of the vacuum are fitted in the slots on the 3 centering rings and fixed with screws. The fin system is driven into the body through the slits opened on the motor section 2, and the system is fixed with screws through the body to the centering rings.
Recovery subsystem. Parachute was preferred for recovery system. There are 3 parachutes in our rocket. These are main parachute, drag parachute, and payload parachute. Conical was chosen as the parachute design. This is due to its simple design and relatively high drag coefficient. Parachute diameters are calculated from this equation. This equation is specialized for round parachutes. Main parachute consists of 12 cores. Drag and payload parachute consist of 8 cores. Parachute material is ripstop fabric. Extra strips are sewn to the joints of each core. Joints gain extra strength with these strips. The rope length was chosen as 1.5 times the diameter. The reason for this is that the drag coefficient increases with the increase of the rope length. This increase becomes negligible after 1.5 times the diameter. Separation system. We used black powder for separation. The reason for this is that high force is obtained with small system. There are a total of 4 slots for black powder on the avionic covers. 2 will be fired at the apogee and the other 2 will be fired at the specified altitude. The explosion will push the payload and parachutes out of the rocket.
At the beginning of the project, we wanted to design the vehicle within the capable of landing with motors and propeller for our mission. But we couldn't do this because of the pandemic effect in our country. After that, we preferred the easier method of the parachute landing system. Payload shared the data within ground station here. Here is the final version of the payload section just before the flight. First progress update, we focused on the 3 commercial system for our computer. However, since ordered products at problems at customs, so the team developed their own flight computers. Finally, we are used 2 different student research and 1 commercial system in avionics section. The RRC3 are our commercial altimeter. For the student research computer, the main flight computer purpose can control the deployment system. The purpose of the other one is the generally receive the only altitude and the position information from rockets and share with the ground station. Those are the payload and the flight computers. For students research one has a same subsystem and the same software library. All power subsystems are different for flight computer and the payload section.
Rocket integration strategy. Kızılırmak version 10 consists of 4 main sections, which are the motor section, main parachute section, the avionics section, and the nose section. The nose section consists of 2 parts. The first is a nose cone, and the other is a tubular body part. These 2 parts will remain integrated throughout the flight. For this reason, the shock cord to be connected to the eye bolt in the nose was made before integrating, and the parts were combined with 4 rivets. A drag parachute, payload, and the payload parachute were placed inside the nose section. The avionics section and the main parachute section will also remain integrated throughout the flight. These sections were fixed with 4 and 4 screws from outer body to the bottom cover of the flight computer after the flight computer is placed inside the avionics section. In this way, the avionics section, the main parachute section, and the flight computer will remain integrated. After assembly, the shock cord of the main parachute was connected to the avionics section, and the engine section were placed inside the main parachute section together with the parachute. The main parachute section and the motor section, which are separated from each other during the flight, was assembled together with the aluminum connection part, which was also be used as a bulkhead. The aluminum part was fixed to the motor section with 8 M4 screws. The orientation of these screws on the radial axis consists of 8 equidistant spacings. When rocket assembly is fully completed, the motor was placed on the motor block and the boat tail was mounted. To ensure that the motor does not slide down when the rocket is on the ramp, the motor was fixed from the front with a Whitford screw. Since the hole diameter of the boat tail is larger than the diameter of nozzle, smaller than the diameter of motor case, the motor holds by the boat tail. Mission concept. The rocket will reach the apogee in 24 seconds. The first separation will be at the apogee. Payload parachute, and the drag parachute will come out here. The payload will descend at 40 feet per second. The rocket will descend at 86 feet per second. There will be second separation at 1640 feet. The main parachute will come out here. The rocket will descend at 34 feet per second. The rocket will land 188 seconds after the launch. The payload will land 328 seconds after the launch.
These are our test management leaders. All of our tests were done in the planet date range. Firstly, a safe environment was created and all tests were carried out carefully. The ripstop fabric was used as parachute fabric in test and production. Then a load of 25 kg was released from a height of approximately 15 meters for testing purposes. No deformation was observed in parachute fabric, parachute strings, or connection points. An explosion with enough power to open the nose cone is created at this point and at the desired altitude. The mechanism and the materials used are designed not to damage structure, cables, or shock cords inside the rocket. The pressure test for bulkhead, it has been observed that it can withstand more than 910 kg of load. The expected maximum load during flight is 470 kg, which gives us a factor of safety of nearly 2. NDT was applied after the step test was performed on Kızılırmak V10 rocket. Non-destructive testing is the type of inspection that does not harm the integrity of the material or part to be examined. The validity of this examination is based on the result of destructive examinations. The flight computer and ground station were operated for 30 minutes. Telemetry format with data from task load per second. The sensor data required for the package number, the altitude sensor, the GPS information, and the separation mechanism were sent to the ground station in a stable manner. The 2021 IREC process was very exciting and full of new experiences for us. We regularly participate in Technofest rocket competitions, which have been held in Turkey since 2018 every year. The launching of rockets in this competition made by Rockets & Company in their launching facilities. We are grateful to Rockets & Company and all our sponsors and who provided us this opportunity despite the pandemic conditions.
6th of May, we launched our rocket for test flight in the Rockets & Company test area. As you can see here, we are using the EOS camera for recording the whole flight and for tracking our flight path. When rocket comes to apogee, altimeter works lately, so there is a problem over here. Probably this problem is about the altimeter algorithm or our pressure holes on the rocket tube. This is the 20 meters per second for all flight.
Rocket touchdown 20 meters per second. Node weight on body tube. Thank you for watching our presentation.